everyone. Welcome back to our session today. We'll be picking up right where Gibran had left us off last week. We'll be continuing some of the topics first, and then we'll move on to a dedicated office hour with QWorld to answer any queries you might have and any doubts you might have for quantum fundamentals. And with that, let me pass on to Rumlah Amer. She is the representative from QWorld who would be helping us with quantum teleportation and a couple of other topics today. The stage is all yours, Rumlah, and it would be great if you could start off with a brief introduction and then move on to topics you have in mind.
Hello, everyone. Hope everyone is having a good day. I'm Rumlah Amer, and today I'll be talking about quantum teleportation and Grover's algorithm. So let us begin with quantum teleportation. So here we have this scenario where Alice and Bob are spatially separated. Alice has 2 qubits and Bob has a single qubit, such that Bob's qubit is entangled with one of the qubits of Alice, right? And this state psi is an arbitrary state given as alpha 0 plus beta 1, right? And the entangled state is the Bell pair, which is 1 upon square root 2, 0, 0, plus 1, 1 state. Okay, so the idea is that Alice wants to transmit her qubit psi to Bob, and she does so by applying some measurements on her set of qubits, and then she measures her qubits. And the whatever outcome she gets, she sends to Bob by classical channel. And once she sends it to Bob does some measurement on his qubit, and then the result is that he gets the state psi out of it, right? So we'll go through the protocol and we'll see how it goes. Okay, so at the beginning of the hold on. So okay, so at the beginning of the protocol, the state, the quantum state, the combined quantum state is represented as state psi tensor product of with the Bell pair. Where psi is just alpha 0, beta 1, tensor product structure. Then we have 0, 0 plus 1, 1, which is the Bell pair, right? So sometimes I'll be writing just directly without tensor product, and essentially it goes like we can assume that when I'm writing 0, 0, that means there exists a tensor product structure between 0, 0. And we can expand on this. We can expand this expression. And what we get is 0, 0 plus alpha 0, 1 plus beta 1, 0 plus beta 1, 1. Okay, so the qubits represented in purple belongs to Bob, and the one in black, they belong to Alice, right? And so Alice does some measurement on her qubits. First of all, Alice applies C naught on her set of qubits. And Bob's does nothing to his qubit. It remains the same. So the first qubit is the target. Sorry, control. First qubit is the control, and the second qubit is the target. Control qubit, and second qubit is the target qubit. So So when Alice has the first qubit is 0, the second qubit remains the same. And when the first qubit, Alice's first qubit is 1, she applies NOT operator on the target qubit. And after doing that, the second operation that she applies on her qubit is that she applies Hadamard operator on the first qubit. So the first qubit is 0 over here, right? So when she applies Hadamard operator on it, it becomes the plus state. With the amplitude changes as well, right? And in the second state, exactly, you have now in this state, the first qubit is 1. So when she applies Hadamard on 1, she gets a negative state. Okay. And in the negative state, we get a negative sign over here. And similarly, in the last state, we have again 1. Okay. So we can so we can rearrange that, and we see that we can take 0, 0 Alice's qubits out. So we get alpha 0 plus beta 1. Then, so we are taking common 0 from here, and we are taking common 0, 0 state from here. And then we are taking 0, 1 common from here, and 0, 1 common from here. So we get 0, 1, alpha 1 plus beta 0. We get 1, 0 common from here, and again 1, 0 common from here. So we get alpha 0 minus beta 1. And lastly, we have 1, 1 state over here, and we have 1, 1 state over here. So 1, 1 and alpha 1 minus beta 0. Okay. Okay. So now after doing these two operations on her set of qubits, Alice measures her qubit. Alice measures her qubits. And she gets the outcomes with equal probability, which is 1 over 4. The outcomes would be 0, 0, 0, 1, 1, 0, and 1, 1, right? Now Alice sends her bits So once Alice measures her qubit, what happens is that the entire superposition that collapses and Bob's qubit also gets fixed, right? And so Alice sends her. So Alice sends her. Yes, Alice sends 2 classical bits. The outcome that she received, that she got after the measurement, to Bob, right? So if Alice sends 00 to Bob, if Alice sends 00 to Bob, so Bob's state gets fixed as alpha 0 plus beta 1. As you can see, how the representation of the quantum state was before the measurement. So if Alice gets the outcome 00, this will be this represents the Bob's state, right? And if Alice gets the outcome 01, Bob's state becomes alpha 1 plus beta 0. Okay, so okay. And then if 1 0, then Bob's state become 0 minus beta 1. And lastly, if the output is 1 1, then Bob's state becomes 1 0. Now, once Bob receives these bits, classical bits, and based on what he has received, the bits, he will apply some measurements on his qubit. So if he receives 0 0, he will not do any operation on his qubits. He will leave it as it is. So we represent it as identity, which essentially means that there is no operation on just identity, which essentially means that there is no operation on his qubit, and the state remains the same as it is, right? And in a similar way, if Bob receives 0 1, that means that he needs to apply X operator, which is the NOT operator. So he applies the NOT operator on his qubits and he flips the qubits. So he will get alpha 0 plus beta 1. And similarly, if he receives 1 0, that means he needs to apply Z operator, which induces a phase over the 1 qubit. So when he applies Z to 0, it remains the same. But when he applies 0 to 1, he will get the output is minus 1 qubit. So minus signs cancels out, and he will receive exactly the same state psi. And in the last case, if Alice sends Bob 1 1 bits, then that essentially means that he needs to apply X operator and then Z operator. And first he applies X operator, which gives him 0 minus beta 1. Then he applies the Z operator, which essentially gives him 0 plus beta I qubit, right? And in all 4 outcomes, in all the possibilities of the outcomes, when Bob applies his measurements, when Bob applies his operators, the output is exactly state psi. So by just looking at this algorithm, as you could see, by this protocol, you can see this thing that Alice has first applied the C naught operator over here, then she had applied Hadamard operator on her first qubit. Then she measures the 2 qubits, and she sends the 2 bits, the classical bits, which are the output of her measurement, through a classical channel to Bob. Once Bob receives it, there is this controlled X operator, and then the Z operator. And the outcome is that the Bob receives exactly the state which Alice held. right? So using a priori entanglement, so the idea is that Alice and Bob has two qubits which were entangled. So using entanglement and sending two classical bits by classical channel, Alice transmits her qubit state psi to Bob successfully.
Rumala,
Yes.
can you also explain the notebook from the QBrunch, quantum entanglement and protocol section of the notebook, where you can just explain the concept mentioned here as the part of the quotes?
Yeah. So
If it is not with you, I'll quickly share for 2 to
no,
3
I
minutes.
have this. Hold on. Let me quickly just go through it. Okay. So here's the material of the QBrunch. It was shared as well. This is QBook. And so over here we have this quantum teleportation algorithm. Sorry, quantum teleportation notebook. Can you guys see my screen?
Yes, we can see this. Oh, yeah.
Yeah, okay, great. So this is the notebook that has been provided, and it contains the quantum teleportation protocol, and the protocol has been discussed in detail over here. Exactly like I earlier discussed that this is yes. So I am using the names Alice and Bob over here in the notebooks. We have the names Asia and Balvis. And exactly as I discussed earlier, there are two qubits. Asia has two qubits and Balvis has a single qubit. Q1 and Q2, Q naught are actually entangled, right? And so first Asia applies C naught operator, and then Hadamard operator, and then measurements. So here are the measurements, which she sends the two bits to Bob, to Balvis in this case, and then Balvis applies operations based on the qubits, based on the bits that he receives. Okay, so there are very interesting tasks which are given with each operation in each idea. You should go through them. The solutions have also been provided just below each task. So for example, this is the task 4. And so you are supposed to write your solution, your code over here, and then run it. And the solution has also been provided over here, just in case if anyone wants to verify it, or if anyone is struggling with it. You can also post on Discord, where we will get to your queries. And don't forget to, if you're using Google Colab, don't forget to run this hidden cell before you actually go through the teleportation notebook. Okay. So next topic that I would like to talk about is the phase kickback effect. Okay. So we will begin talking about phase kickback by noticing the effect of C naught operator on the state 0, 1. So consider the state 0, 1, and we apply Hadamard over the state 0, 1 to get these states into superposition. And when we apply Hadamard on 0 state, it gives us plus state. And when we apply Hadamard on the 1 state, it gives us plus state. Oh, sorry, minus state. Okay. And as you can recall, the plus state expands out to be like 0 plus 1 divided by under root 2. Then we have 0, 0 qubit minus 1, and then divided by root 2. Next, we apply C naught operator, such that first qubit is the control qubit and the second qubit is the target qubit. So let me expand this as well. So when we are working with it, it becomes easier. Okay. So the first qubit is the control qubit and the second qubit is the target qubit. And when we apply C0 operator, it gives us, so 0, the control qubit is 0, so the second qubit remains the same. But when the control qubit is 1, we apply NOT operator on the target qubit. Okay. And it is interesting to know that we can just take these 0 qubits common. Okay. And so what we notice is this, that in the second qubit, the qubits are flipped. Now we have a negative sign with the 0 qubit, right? And so if we take this negative sign common, and we take this negative sign out, what do we get? We get okay. So since the states in the brackets are the same, we can write it like this. And as I have mentioned earlier, that when I'm writing brackets like this, that means there exists this tensor product structure, right? Okay. So it is interesting to note this. So we begin with 0, 1 state, and we applied Hadamard on it. And then after applying Hadamard on both qubits, we applied C0 operator. The C0, the effect of the C0 operator is on the second qubit, as the second qubit is the target qubit. And we get this negative sign over here, but this negative sign, this phase over here, it actually translates to the first qubit. And now when we apply Hadamard again, we get 1, 1 state. So this effect of getting the phase being translated to the first qubit is actually known as the phase kickback effect, and it is very useful when we are working with quantum algorithms. So let us talk about it in terms of quantum algorithms. So over here we have this state A, and this auxiliary qubit B. This circuit is represented as B of F. And then we have B F of A. So over here, A is any n qubit state. Right? And the function f is being defined as 0, 1 to n. There's a Boolean function that is being mapped onto 0, 1. And the operation of this B of f is defined as P, which maps as to as A, the state A, which is an n-qubit state, it remains the same. However, in the ancilla qubit, we get this XOR, which is a bitwise a modulo function. Okay. So over here, this is the XOR function. So we consider this effect of this circuit P of F when we consider our ancilla qubit to be minus a state, right? So let minus state be, let B be equal to the minus state. So it is interesting to note that this XOR operation is being applied on the within the ket on the classical qubits. Sorry, on classical bits, right? So we are fixing our B to be minus state, and then we are seeing the effect of this B of F over A and minus state. Now we can write the state minus in terms of classical basis, computational basis, like 0 minus 1, 0 qubit minus 1 qubit over square root 2. When we further, so the effect of B of F of A by definition is that it remains the same, that we get the same state out. So A remains the same, where else we apply B of F over 0, then 1, right? We can write it in the Keth notation. The outcome of this operator B of F is going to be 0 XOR F of A, then 1 XOR F of A. Now we need to, so as we have discussed this before, that F is a function that actually is a Boolean function that maps to 0 or 1. So there exist two possibilities, that either F of A is equal to 1 or F of A is equal to 0. So let us consider both cases, that F of A is equal to 0, then B of F is just going to be it will remain the same. What essentially I have done over here is that I have replaced this F of A with 0. So when we take the XOR of 0, XOR 0, it will give us just 0. When we take XOR with 1, XOR 1 XOR 0, it will give us 1 again. So it remains the same, it does not affect it. However, when F of A is equal to 1, then this will become one XOR 1. Which will give us 1 minus 0 qubit over square root 2. Okay, so it has induced a phase over these two qubits, right? And so we can generalize these two cases when f of a is equal to 0 and f of a is equal to 1, and we can just directly write it as f of a minus state. So essentially what I have done over here is that I have taken this minus phase out, right? And it will give us back this state A tensor product with 0, -1 qubit over square root 2, right? And so I have generalized these both two cases, and we can write it like this over here. So essentially what we have done is when we apply this operation B of f over these states, so the operation of B of f was on the ancilla qubit, and that operation has been shifted to the face of the entire state. Now we have -1 to the power f of a. So when f of a is equal to 1, and when f of a is equal to 1, this will become minus, which essentially what we saw when we discussed that both the cases separately, right? So this effect, so by applying classical transformation on a quantum circuit with when our ancilla qubit is initiated to minus state, what we have done is that we have seen its phase kickback effect, that it gives a phase over the entire quantum state. And this is very useful when we are working with quantum algorithms, which we will see very soon with the Grover's algorithm as well. Okay. So we will start talking about, we will also be talking about Grover's algorithm. Let us start talking about Grover's algorithm. So the problem statement for Grover's algorithm is that given a Boolean function f, which maps n bit strings to bits, classical bits 0 or 1 as a black box, we need to find a string such that we need to find a string x over here, an n bit string, such that f of x is exactly equal to 1. So the Boolean function has been given to us as a black box, so we do not know how the function is working, and so it gives us no insight about the structure of the problem, right? A structure of the function. So, and now we need to find a string such that f of x is equal to 1. So this is an example of unstructured search problems, where out of all these outputs of this function, some of the outputs are equal to 1, as we can, are 1, and we need to find out here which outputs are actually equal to 1. So one example is when we fix the number of bits in the inputs to be equal to 3. So once we fix n to be equal to 3, we get exactly 2 to the power 3 bit strings, total 8 strings, which are 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, so on and so forth. And this is one example that out of all of these, some output is actually had been equal to 1. And now we need to find out that which output or which element is actually equal to 1. And classically, when we solve these unstructured search problems, it gives us a classical complexity of 2 to the power n. But when we are working with the Grover's in quantum algorithms, and we are using Grover's algorithm to solve the problem, it gives us a quadratic speed up, and it gives us omega of square root of 2 to the power n, right? Okay. So we are going to, so we are, when we are talking about Grover's algorithm, we are going to use n qubits. And at the beginning, of this this quantum algorithm, we are going to apply. So initially, whenever we are working with quantum algorithms, the qubits are initialized to 0. So all n qubits are being initialized to 0 over here, and then we apply Hadamard to each qubit, as it has been shown over here. So we apply Hadamard to each qubit, so that we get the entire quantum system in a superposition. So we have all possible input strings of length n in equal superposition, right? And so equal superposition. So what essentially it means that the amplitude of each basis state is said to be 1 over n. And we iterate the algorithm several times. This algorithm can be thought of as in two parts. The first one is that we make a query and we apply a query oracle operator to the qubits, which essentially does is that it flips the sign of the amplitude of the state that corresponds to the marked element. Okay, so here we are talking about in terms of marked element. So marked element is the string maps to 1, right? And then we apply inversion operator, which essentially do by applying diffusion matrix, and the amplitude of each state is reflected over the mean of all amplitudes. Okay, so when we apply, so all the qubits are being, so this is a circuit representation of the Grover's algorithm. So there's n-select qubit also involved over here, which is not being represented, but we will be using it when we can suppose that it is also included. Okay, and so we have these n qubits and qubits that are being initialized to 0, and we apply Hadamard over here to get them into equal superposition. That's essentially what has been done over here. So 0 to the power n essentially means this is an n length string, bit string, where each bit is 0. Okay, and we apply Hadamard on each qubit. So we get this new state, which we are calling h, upper lowercase letter h, such that the amplitude of each basis state is exactly 1 over under root n, and the summation is over all basis state, where x represents all the binary strings of length n. So here this uppercase letter n, a capital letter n, represents 2 to the power n, which is the number of strings in n. Okay. Now the Grover's the Grover operator that has been represented as this minus h to the power, this is tensor plotted n, which essentially means that the Hadamard is being applied on all the qubits, right? Z naught, and then again Hadamard being applied on all the qubits, then ZF. So this is the way that I'm reading it, but when we apply it, so essentially it means that the first Z of F is Z. When we apply Z of F on any quantum state X, it gives us X and X. So this is the phase kickback effect, right? Where else? So the idea behind this operator Z of F is that whenever this input X is being marked, the F of X is equal to 1. When X is not marked, it is unmarked, then that would mean that F of X is equal to 0. So F of X is equal to 0. So F of X is equal to 1 when X is marked, and this is equal to 0 otherwise. So this operator will only induce this space over the input if the string x is actually marked. What essentially it means that f of x is equal to 1, right? Now z not x is defined as minus x if x is equal to the 0 string, and it remains the same if x is not equal to the 0 string. Essentially what it means that, so we can see the matrix representation of this operator, right? So z naught will be defined like -1, 1, 1, so on and so forth, 1. So we have on the diagonal entries, we have 1. And on all the off diagonal entries are equal to 1, are equal to 0. Okay. So essentially it means that we have this identity matrix -2 zero operator. So here's a very nice representation of z naught over here. So when we are talking about the operator G, so when we apply this operator G on the state H, what this part does is it flips the sign of marked elements. Marked elements, or you could think of them as strings, right? And where else this part ensures that we have inverted all the elements over the weighted mean. So this will provide inversion over the mean. And we will get back to it later on, that what exactly do we mean by inversion over the mean, right? So first, let us go through these operations, how exactly we are applying this operator G. And so before we actually go on about it, one interesting thing that I would like everybody to notice is that this state H, which is the equal superposition over all possible inputs, actually can be divided into two sets, right? So what essentially what we do, so in this all basis elements, in all these basis elements of X, right? So there are some strings that are marked and there are some strings that are unmarked. By marked, I essentially mean, so let me write it so that there's no confusion. Marked strings, that means that X such that f of X is equal to 1. And unmarked, so I'll be using these words frequently, so I want to make sure that everybody is on the same page. And unmarked strings will be those strings such that f of X is actually equal to 0. So we can divide the entire set of strings and bit strings into two sets, such that one set contains the marked strings and the other set contains the unmarked strings. And let us call them A. So let us such that f of X is equal to 1. So set of marked strings. And let us represent the cardinality of this set by this small letter A. So what exactly do I mean by cardinality of the set? Is the A is the number of strings in the set A. Okay. In a similar fashion, we define another. In a similar fashion, we define another set B, and this will contain all those strings which the function maps onto zero. So f of x is equal to 0. That means set of unmarked strings. And we can label the cardinality of this set as small letter b. So b is the number of string in the set p. Now, once we have defined these two sets, what we can do is now we can restate, we can represent this H in terms of the set A and B, right? And how exactly do we do that? First, we need to define these. We need to represent it in the ket notation, right? And set A, and similarly we define B, which is the superposition of all unmarked strings. Okay. So I will quickly discuss the idea behind the algorithm, and we will move on to the Q&A session afterwards. And so we have this. Now this state is actually being defined in terms of A and B. So the idea behind this defining it this way is very convenient when we represent them on a unit circle. And we say that this state is actually the B state, which is the equal superposition of all unmarked states, and this is the state A, which is the superposition of all marked states. And when we apply G over this state H, it induces phase kickback effect on the marked states, which is kickback on the state A, which are marked, right? And the first Z of F will induce the phase kickback, and then we do the inversion about the mean thing. And the idea behind this is that exactly that if this is the state psi, and we apply G on the state psi, what essentially it does is it rotates the state in the unit circle by 2 theta, right? Because as you can detect somewhere over here, this is this state H can be represented in terms of sine theta A and plus cos theta B. So the effect of operation G on state psi is that it rotates the state psi counterclockwise by 2 theta, right? And the idea is exactly this, that we keep rotating it until this state psi is more aligned to with sorry, let me not write this. Okay, so it is more aligned with this vertical axis towards the A state. And so we actually, essentially what we are doing is we are just we are just increasing the probability. We are just increasing the amplitude of the marked strings. And by doing so, what we are doing is we are decreasing the amplitude of the unmarked strings, set of unmarked strings. And so there is also this critical part, which I would strongly recommend you to go through the notebooks and go through the concepts that how many times this operator G should be applied, right? So I'll just take quickly, I'll just take 2 more minutes before moving on to the live Q&A session. So as you can see in the circuit over here, so this is our operator G. And again, this is again our operator G. So this operator is being applied multiple times. So how many times? K times. So this is a very essential part of the algorithm that we need to determine how many times should we apply the operator G so that we can exactly get the after which when we do the measurements we get the set of marked strings, right? So otherwise, because if we keep applying the operator G, then it will move on towards somewhere away from the state A, right? And okay, so you should, so there is this, so due to shortage of time, I'll try to stop here. If you have any questions, you should ask me. One more thing before moving on to the live Q&A session, I would like to go through is that this okay. Okay, so here on this link, QBook 101, which is available on QWorld's website, this is chapter 4, 4.3 is the Grover search algorithm in Qiskit, which essentially starts talking about the inversion about mean, then it moves on towards the Grover search 1-qubit representation and its implementation. So I would highly recommend you to go through these notebooks and work out the problems and work out the tasks that has been given to you in these notebooks so that you can build on top of it and understand the entire algorithm. So I'll stop here and I'll move on towards the live Q&A session. Sure.
Why does measuring Alice's qubits turn them into classical bits?
So once Alice measures her qubits and she sees what her result is, what her outcome is, she sends these two classical bits to Bob, right? So the whole idea is that she wants to transmit her qubit state psi, where the amplitudes are just alpha and beta, with the Born rule over them that alpha square plus beta square is equal to 1. So she wants to transmit this quantum bit, qubit, to Bob without actually utilizing any quantum channel, right? So essentially what she does is she measures her qubit, and whatever outputs that she sees, she sends two classical bits to Bob. And based on the classical bits that Bob receives, Bob then applies some measurements on his qubit, and the resulting state is exactly the state psi that I just wanted to send to Bob in the first place. I hope that answers your question.
Okay, thank you. This is Prachi from Boston. Does it have anything to do with how measurement forces the qubit to assume a classical state?
So once Alice receives Alice's superposition collapses, she does her measurement. She can receive her outcomes in the classical register, right? And then she can send those classical bits to Bob. How does the choice of the initial state B minus 1 B wrangle lead to the phenomenon of phase kickback in the function evaluation of B of F? So so during phase kickback, what we were seeing over here was that we applied this classical operation over here, like XOR over B, XOR F of A, right? So it is this is a very nice exercise that you should try to do this thing, that you should consider the case when B is the plus state, right? So what happens if instead of using the negative minus state, we use plus state, right? And what will happen is that it will not somewhere over here when this is when there is a positive sign over here, it will give us back the plus state exactly. It will not induce a phase kickback, right? Because if there is a plus state over here, so you can see this. So I'll get back to your question. I am just building on top of it, that if there was a plus state and you will get 0 XOR 1 plus 1 XOR 0, again 1. So again 1. So what essentially happens is that you will get 1 plus 0 square over square root 2, which is essentially just the plus state. It does not induces any phase on the entire quantum state. So the interesting thing happens when we choose this ancilla qubit to be equal to a minus state, because when we are choosing this minus state, so in the case when f of a is actually equal to 1, what it does is when we are over here in this part of the computation, so we do this 0 XOR 1, so it gives us the output is exactly 1. So let me write it down. So xy 0 0 1 1 0 1 0 1 and x or y. So x 0 0 will give us 0, this will give us 1 1 and then again 0, right? So when we are doing this computation, this XOR operation being applied over 0 and 1, so we get 1 out of it. And when we apply this XOR operation over 1 and 1, we'll get the output 0. And this now, as you can see over here, the negative sign was, the negative phase was attached with the 1 qubit. But over here, after this XOR operation, now the negative sign is being there's a positive phase with 1, right? Because of the negative sign, we have chosen negative ancilla qubit, negative minus state as our ancilla qubit. So we get this sign flip over here, and then that sign can be taken out, right? And so for both possibilities of the function, f of a being f of a is equal to 0 or f of a is equal to 1, we get this very nice phase over the entire state, our input state, after applying B of f. I hope that answers your query. If not, please do let me know.
We've got one question that came in. Since quantum teleportation involves transferring the state of a particle without physically moving it, how does it comply with the non-cloning theorem? Can you elaborate on the destruction of the original state during the process? And that's from Danso.
So when we are going through these operations, essentially what Alice has done is that she has first applied C0 operator and then applied a Hadamard operator on the first qubit. And the first qubit was the state psi that she wanted to send to Bob, right? And we saw over here that because of the normalization, how it happens is that Alice has access to both of her qubits, right? And over here in this step, essentially what is happening is that we have this normalization constraint on the entire quantum state of the circuit, right? And it ensures that when we take out 0 0 qubits, so we are left with this state which is basically Bob's qubit, right? So, and Alice's qubit has now been in a equal superposition, as you can think of, in terms of 0 0 0 1 1 0 1 1. So she has not cloned her qubit and sent it to Bob. Rather than that, there were some very straightforward quantum operations that she applied to her qubits, out of which one qubit was actually entangled with Bob's qubit. So the idea is that she has utilized the resource, which is entanglement in this case, to actually transmit her entire qubit to Bob, rather than actually cloning it, instead of cloning it, right? And so as you can see from the representation of the quantum state of the entire circuit from over here, when she major for qubit, there are only these 4 possibilities. So these 4 possibilities, which is 0, 0, 1, 0, 0, 1, 1, 0, and 1, 1 state. And there was an equal probability, which would be 1/4 of getting these outcomes. Right? So her quantum state, which was comprised of like 2 qubits, that actually also collapses to either 0, 0, 0, 1, 1, 0, 1, 1. I hope that answers your query.
Yes, Danso has replied it has. Okay, so I'll take the final question.
Sure.
This is from MC. If Bob knows which operator to use to get the pi state, then he also knows the original state. Then what is the utility of the algorithm in quantum teleportation?
That's a very good question, actually. So Alice, the only information Bob has is this: when he's going to receive the 2 classical bits from Alice, then based on those 2 classical bits, he's going to apply some operations, right? But the state phi, but the amplitudes alpha and beta are not being specified, right, to Bob. So Bob does not know a priori what the amplitude of qubit 0 is going to be, or the amplitude of the qubit 1 is going to be, right? That information was with Alice only, right? That qubit was with Alice only. And as we can see after the entire protocol, that this is exactly the same arbitrary qubit that we begin with. The state psi, when Alice had this qubit in her lab, this was exactly was alpha 0 plus beta 1. Bob had no prior information about it, that what the state is, what the amplitudes are, and so on and so forth. The only information that he had was once he's going to receive. So there are 2 actually interesting things that are happening. Okay, so this is the state psi that Alice had, right? She applied some operations on it. And after doing those operations, C0 operation and Hadamard operation, what Alice does is Alice measures her qubits. Once she measures her qubit and her outcomes gets fixed, that essentially means that Bob's state also gets fixed, right? And then she sends these 2 classical bits to Bob. And based on those 2 classical bits, by looking at them, by knowing the information they carry, then Bob is going to apply some operations on his part of the qubit. I hope that clears that answers your query. If not, please do let me know.
Thank you very much. I think that wraps it up for today.
Thank you so much.
Thank you so much, Katie, for having us. It was an amazing session.
Amazing. So thank you, everyone. That was a great start to the week. See you guys next time.